Welcome to Catalyst Conversations, a podcast hosted by the FedEx Institute of Technology at the University of Memphis. Here, we bring together leading thinkers, researchers, and innovators whose work is sparking new possibilities across disciplines. From energy and defense to agtech, computing, and emerging technologies, each conversation explores the ideas, breakthroughs, and real-world impact shaping our shared future. At the FedEx Institute of Technology, we don't just talk about what's next. We build it, test it, and connect it to the world. Let's get started.
So we're super excited to have everyone here. I'll let you go into more detail, but we're going to introduce Hrant Gharibyan, who is the CEO of BlueQubit. And I'll give you a hint, might have something to do with quantum computing. And we're super excited to hear all your insights on using quantum computing for discovery and research. So thank you.
Thank you. Thank you for the opportunity to give the talk and share some of the work we're doing and talk generally where the quantum technology is and how it's going to affect scientific research as well as commercialization in the next decade to come. So I am by training a theoretical physicist and who turned into quantum algorithms researchers throughout my academic career, working at Stanford and Caltech, and also during my postdoc years at Caltech working closely with Google, who have one of the best quantum devices. Ecosystem is very rich and it's moving really fast. So hopefully this will be helpful for some of the researchers and technologists in the room. So I'll say a few words about what's BlueQubit, what we do as a company, and then talk about basics about quantum computing specifically, and the progress in building a quantum computer, and also talk about applications to scientific research and discovery, which is more of interest for a group. And then I'll stop in certain points to take some questions. So make it very informal. So we are a quantum software company. So all we do is algorithms development and research and testing. Our team is composed of quantum PhDs and experts in computing, like high performance computing, people who know how to run large jobs on HPC clusters, GPUs, CPUs, and currently QPUs, which is quantum processors. And the team is composed of people from Google, IBM, Quantinuum, and Stanford and Harvard. Very big mix of people. So we have actually a software platform that you can go in and test out. So if you have an appetite for programming, you can write a quantum program. And we support a lot of popular languages such as Qiskit, that was developed by IBM, or PennyLane by a Canadian company, Xanadu. That's some of the most popular libraries for writing quantum programs and testing them and running them at scale. And then in our platform, you can actually access some of the best quantum computers in the world, like IBM systems, Quantinuum systems, QERA systems, which each of them use different approaches to building a quantum device, different type of qubits. We orchestrate all of these workflows. We do a lot of simulations, and then we have a lot of advanced software and libraries that came out of research that we package and put it in the platform for quantum researcher community at large. So, all right, let's see, why do we need to build a quantum computer, right? Our normal computers work pretty well. Why the hell we need to invest hundreds of millions or potentially billions of dollars to actually build these devices? And what's the main advantage we can get from those? And the investment happens on government level by DARPA and DoD and NSF, all the way to companies like Google having a huge quantum team, or Amazon starting a quantum team, or VCs investing in quantum startups. And the primary reason that this is going to be the biggest disruption in the way we do computing. So most of our modern world, all the security, operations, everything is based on normal computers. Phones, laptops, screens, everything is based on a digital setup of the computing, where you have a strings of ones and zeros, and then you build abstractions on it. So every device we have is essentially if you go deep down, what it does is manipulates zeros and ones and stores them and moves them and then performs operations on them. With quantum computers, there's this crazy thing. If you go and try to do computation in an atomic scale, like with electrons or ions or like different like atomic, like smallest tiny materials, things behave very differently compared to the normal world. And that's known as quantum mechanics. We have known this for 100 years, since like 1920s. And a lot of like physics has been built on it. But one thing that it allows, these things that information can be both 0 and 1 at the same time. In a quantum realm is called superposition. But what it allows to, if you are able to harness that for computing purposes, you can essentially parallelize a lot of normal computing to unprecedented like exponential scale. So instead of single bit string storing and moving that had only like 100 bits, you could manipulate with a 100 qubit device, you can manipulate 2 to the 100 possibilities. That is like larger amount of possibilities than atoms in the universe. So you can never parallelize with a normal classical computing to a scale that quantum computers can parallelize. And that's really like powerful and exciting. And that's basically what warrants all the investments and the exploration. Because if you can do it, you can actually solve problems that would be impossible to solve with the normal computers. And I will primary talk discussion of this talk will be around some of the problems that we know how to do. So in terms of like a qubit, as I briefly said, I can kind of illustrate it a little bit. So normal computing devices can be 0 or 1. So those are the two endpoints. 0 is the up and the 1 is the down point. If you create a qubit, either from some ions in some state or some superconducting material, if you make it quantum and make it stable quantumly, it can be pretty much any point in the sphere. You can manipulate, and then when you measure, only then you find one of the outputs. But before you measure, you can conduct operations on this kind of infinitely large space of possibilities. And that's what nature tells us. That's how nature works in an atomic scale. Now we want to kind of harness it for computing purposes. First attempts to build a qubit was in like 1990s, actually. In MIT, they created what's known as NMR qubit. It's a spin qubit. Later on, more government funding, NSF and others supported, and the superconducting qubits and trapped ions were created, again in an academic setting. Late 1990s, early 2000s, 1 or 2 qubits were created. And there were only a few qubits, right? There are like a handful of qubits, and some researcher published a paper in Nature. Hey, I created 1 qubit that I can write and read the information out of. But 1 qubit is not really useful for computation, right? It's kind of how 1 bit wouldn't be useful for doing anything. You need to reach certain scale to start solving practical, interesting problems. So quantum algorithms are essentially, the first challenge was to make a single qubit, then to make many qubits. And then once you made a bunch of qubits, then the goal is to run operations on it, like run some tasks, and then initialize at some point of the state, run some operations, and then read out the answer. And those operations are called quantum gates. So these are the ways we control and change qubits. Single qubit gates, like change single states, and then 2 qubit gates make neighboring qubits talk. And that's one of the hardest things to do from operational point of view. Even after you created few qubits, actually running few tasks on it and then reading out the answer correctly was really like hard scientific challenge. And the whole field of quantum computing basically kickstarted at like 2000s, was essentially had a mission to build more and more qubits and more operations. Those are the 2 things that we're optimizing as a community and from industry or scientific point of view. And then once you reach certain milestone, you can start solving problems that are impossible to solve with the normal computing methods or theories or tools. If there are like more traditional computer sciences, a computer scientist, this is essentially what the machine level code looks like. If you write any like operation, if I change the slide on a low level in the computer, what happens? There's a list of operations of bit flips, single bit flips, or 2-bit operations that like translate my action into machine code. So now we are in a machine code level in quantum technology, which is what normal computing was in 70s, where people used to explicitly write machine level code. And yeah, this is how quantum machine level code looks like. It's a quantum circuit. So each of the lines is a qubit, and then each of the operations manipulates, changes the qubits, and then you rotate it with some operations and then or make them talk to each other, different qubits, and then you can build what's known as quantum entanglement, which is the most powerful tool for computing. And the crazy thing is, we're like in this example where you have 11 qubits, essentially with quantum computing, you can turn this 11 qubits to 2,000 dimensional space, exponentially larger space, and that's where the real computational power comes in. So every time you add a qubit, it's doubles the computational power of your system, as opposed to in a classical computing, every time you add a bit, you only linearly grow, and that's what really the difference between quantum and classical. And that's why it's exciting to build quantum machines that actually can do it at scale. So one of the actually main questions when people postulated quantum computers early on, I think first guy to speculate it was Feynman, who was a famous physicist, Nobel laureate, and he wanted quantum computers just to simulate atomic physics and nature. So he was like, oh, nature, when you simulate molecules, nuclear reactions, everything is quantum. So you actually need a quantum computer to study those things effectively. So you need that. But then there was an actual question, are there other problems that quantum computers can solve exponentially faster, not just simulating nature at atomic scale? And Peter Shor was the one who really changed the perspective on this. He had nothing to do with quantum physics. He was a number theorist by training. He was in the math department. And he came up with an algorithm known now famously as Shor's algorithm in 1994, where he said, okay, if I'm allowed to have these computing machines, quantum computers, that can have arbitrary number of qubits and arbitrary number of operations, that suppose somebody very smart builds it and is able to fund it, it's a government or a company, they build it, what can I solve with it that will have a huge impact on society? And he was able to come up with an algorithm that will essentially completely disrupt cybersecurity of the modern world. So most of the world now relies on this algorithm for encryption. Your bank accounts, national security secrets of the government, your credit card chip, all of it is based on this algorithm called RSA, where you multiply two prime numbers, you get a final number. Going backwards is exponentially hard classically. It is believed to be very hard classically. So nobody knows how to revert it. And that's why you have this public key, private key security system all over the infrastructure, all the internet infrastructure of the world. But with quantum computer, Peter Shor came out with an algorithm that could actually solve that problem way, way faster. In fact, he said instead of exponential in number of bits, it will be n to the cube number of quantum operations. So if somebody builds quantum computer really quickly, just figures out how to make more qubits and more operations, they can technically break all of the cybersecurity of the world. And this is why quantum computing has been a primary on the top list from cybersecurity perspective from US government and Chinese governments, because I think there's a race to whoever can build such a machine first will have a lot of strategic information advantage relative to the competition. And yeah, you don't really need to make a weapon out of it, but you can basically decode a lot of secrets that have been encrypted with RSA encryption, which is very vulnerable. So this algorithm really changed the perspective and how usefulness of quantum computing, because just this one use case makes it very valuable. And it was actually a very breakthrough moment because quantum algorithms, it was an example of exponential speed up where you could take an interesting classical, very well-defined problem, cryptographic problem, and accelerate with quantum exponentially. And that was a huge deal. It was a big deal, and it really drove after that the investment on actually building quantum computers has grown substantially. after this result, and many other results followed it, but this is probably the most famous result in quantum. So now we are in an era where we're actually building quantum processors. Like not me, not BlueQubit, but like a lot of our partners like IBM's and Google's and Quantinuum's and others who are really building quantum devices. They're called quantum processing units, and they are quite different. Some of the approaches are pretty similar to the way we build semiconductor processor, like normal processors and CPUs and GPUs, but some are completely different. And we know that once we get to a certain scale of these machines, they will have tremendous impact on scientific discovery and commercial world. So this is one example of a quantum computer that I have seen personally. This is the one by Google Steam. It's actually the real quantum device is actually this big. It's a chip. It's very similar to normal semiconductor chips in normal processors, but it's made out of material that becomes superconducting when you put it inside a cryogenic fridge. So the big thing around it is a fridge that it puts the temperature down to like 4 millikelvin. So you need to go to that regime, and then this chip they have has 100 qubits in it. So technically it has 2 to the 100 possible states it can be in and like can be operated. And one of the hardest things is actually controlling this chip with wires, because you have special wiring that goes into the chip and then that still works at like 4 millikelvin temperatures. So yeah, it's not very easy to build large-scale quantum computers. Required probably a couple $1 billion from Google's budgets to get to the point we're in now. So, and actually another exciting result was that the Nobel Prize this year went to people who scaled up. It's actually very funnily written. It's like creating entanglement in macroscopic scale. They don't say it's for quantum computing specifically, but for creating entanglement in quantum devices. John Martinez and Michael Devery. John Martinez was the previous head of a Google Quantum. Michael Devery is the current head of the Google Quantum. And they got the Nobel Prize for the large-scale quantum device manufacturing with superconducting processors this year, which is quite exciting to recognize. And the big paradigm-shifting thing I was talking about in the beginning, we knew that small things like atom can be quantum, but I think there was a lot of speculation whether one can make hundreds or millions or billions of atoms to be quantum and be coherently like controlled. Essentially, the biggest breakthrough of John and Michael was to show that it's totally viable. Just this requires clever understanding of physics, material design, and hard work over like a decade to actually make it happen and illustrate in real experiments. There are a few other ways to build quantum devices, also super exciting. One is a team that came out of the Misha Lukin's research from Harvard that now is a company called QERA. They have atoms called neutral atoms, which are like tiny atoms. They move around with lasers, and they encode the quantum bit qubit into different atoms, and they can make thousands of them entangle and talk to each other and run operations. Very impressive system, a totally different way to build a quantum processor. And then Quantinuum has probably one of the most powerful quantum processors in the world. It's a private company, but came out of Honeywell's research lab, which is very, very kind of exciting that Honeywell had a research team that has done really advanced like trapped ion research for many years. And then when it became very mature, they spun it out as a separate company. And also they have a 98 qubit system that can run like thousands of quantum operations on it, which is like super exciting. And all of this has been happening in the last year, essentially, like for decades of research and hard work. And last year is kind of a culmination point because we're able to have many qubits and many operations packed in the systems. Yeah, this is a slide about kind of different ways to build qubits. So I talk about superconducting. IBM and Google are in that bucket. They're some of the largest like companies who do quantum computing work, very impressive work. Trapped ions like IonQ and Quantinuum. IonQ is a public company, also building trapped ion devices. And then atoms like QERA is one of the best companies there. And then photonics is yet another direction. Xanadu is a Canadian photonics company. And then Quantum is a Bay Area-based company that they raised like $1 billion, which is pretty crazy for a startup. And they're completely secretive. So one thing that I have no idea how advanced their systems are. They have a totally different model of sharing. All the other teams like Google's and IBM's and Quantinuum's, they are all very academically oriented. Everybody publishes the results. Like everything is openly collaborative. Very similar to what happened in AI in like 2015 to 2020. After that, maybe companies became closed, but most of the players are very open research. Quantum, on the other hand, is extremely secretive, but then they also were one of the top recipients of DARPA award, and they got actually reviewed by serious scientists. So I wouldn't dismiss them, as just kind of a hypey company. They might actually be ahead of a lot of the players right now. Yeah, there were a few major breakthroughs basically last year and a half. One of the big ones was last December. I think Google announced big advancement in quantum error correction. So like error correction is used everywhere. I'm not gonna get too technical about it, but essentially it's very important to be able to build large-scale quantum computers. We have to figure out how to encode quantum information efficiently and safely so we can keep scaling them so we can eventually break cryptography, simulate drug discovery, and solve like very hard problems. But it was like it never was illustrated experimentally in a quantum processor. So last year there was a huge result by Google. It was all over the media. And after that, all of the stocks of quantum companies that were public like jumped by 20x, because I think one big scientific risk in the quantum technology was de-risked by Google team, and now it's actually much more of an engineering risk because they had first illustration of it in an experiment. Now merely needs to be scaled, which is still hard, but it's more of an engineering risk rather than a scientific risk. Yeah, so as I said, in quantum computing, there's two dimensions once you should look: number of qubits and number of operations you can run on a quantum computer. My Caltech advisor, John Preskill, actually coined the name QUOPS, quantum operations, which is analogous to classical computing. There's a term flops, like how many classical operations per second. And like, NVIDIA is like the leading world company with a flop count. Like in quantum, it's QUOPS, like how many quantum operations. And now we are at this point where we have few platforms with few hundred, like 100 plus qubit systems, and they can run like 10,000 operations, like 10 kilo QUOPS. And this is a new era where we can do scientific quantum advantage, study interesting problems in condensed matter physics, in high energy physics, in material simulation, in optimization, like that are like well-defined scientific toy problems. They're not commercially useful yet, but you can show that you can solve a problem that is impossible even with the largest supercomputers in the world. So even with the largest supercomputers running like years, you can't solve something that Google's device can solve in 3 hours. And with a few kilowatts an hour energy, as opposed to like 5 years and like 1,000 gigawatts an hour of energy. Those are niche problems, but the idea is as the devices get bigger and bigger, quantum is going to be solving more and more types of problems, including potentially training AI, doing financial like modeling, doing optimization in supply chain, which is something might be relevant for like FedEx and many airlines and Air Force. And I think this is just a matter of qubit count and the gate count, like QUOPS and qubits growing. And that is now like became an engineering challenge rather than scientific, given the latest developments. So yeah, in terms of scientific advantage claims, and this is a fascinating time, like for me personally, because yeah, a few years ago, I would anticipate it will take like years still to get there when I started the company. I think it happened much faster than I thought. And a lot of it driven by a lot of enterprise interest and investment and drive. And now, like I think from scientific to commercial, we're going to witness it in the next couple of years, essentially 2028, 2029. So in terms of like scientific advantage results, just this year, there's like several papers that like still standing as pretty big claim. One of them came from a company called D-Wave, which has an annealing quantum device. So, and they were able to create a type of matter in a quantum computer that nobody knows how to do it classically. In fact, I think they estimate the type of matter, which is interesting for, yeah, I'm not going to get like into technical jargon. A lot of condensed matter physicists care about this type of matter in academia, in national labs, in research institutions. They are able to create this type of matter like where like classically nobody knows how to do it. And it has been there for like several months now. A lot of classical people thought very hard, and they anticipate if you try to solve it with the large classical exascale supercomputers, if you even buy all of NVIDIA for the next few years, it will take you another 100 years of running to get to the answer. So that is like really like fascinating new result, and it opens the discussion what other interesting problems can you study with this device. Similar claim came from Quantinuum as well. Yeah, very like in a similar domain. And lastly, yeah, I guess I can tell you actually like a little bit about Quantinuum result. Essentially, what they do, it's again condensed matter physics problem. It's a what's known as an Ising model. It's a specific toy model that later can be connected to superconductivity, to semiconductor properties, various like interesting phases of matter that are useful for building materials. But it's a model like on a torus. It's like some geometric setup, and they're able to simulate the dynamics of this quantum system, very entangled quantum system. And they run like simulations. They do the measurement in their quantum device, and then they show that there's no way to get this classically. And they try many different classical strategies, and none of them agrees with each other or with the device, the answer that quantum computer gave us. And they have further experiment to kind of how to validate that the quantum computer gave us the right answer. So this is like in that flavor, I think one of the most relevant for more condensed matter material scientists, like what other interesting problems that are like we can't solve with the normal simulations classically, computational simulations. We can't solve with analytic theories, like it's very complex, like types of matter. Can we use quantum devices to enter that space and probe new types of matter, new ideas for room temperature semiconductors or other interesting properties like with quantum computers. And these computers are now available to researchers, and they're going to be even more available. So like, for instance, Quantinuum, US government, I think DOE just purchased one of the Quantinuum's latest device. So did Singapore's Research Institute, and I think it's going to be available to the scientists in academia. So if there are people who are interested in condensed matter simulations, I think those systems would be a completely new tool available for scientific discovery. In a similar vein, with a much more bigger popular like advertising and marketing, result came out of Google as first example of verifiable quantum advantage. And they also looked at an interesting material science problem on their device. The device I showed earlier in a talk, which sits in this cryogenic fridge. And again, they solve a very interesting material simulation problem. They later related to actually doing NMR in molecules. So it might be actually commercially, they kind of illustrate how the commercial path will look like, where like NMR experiments in pharma, in defense, in automotive, and material discovery teams, how you can leverage this quantum device to learn properties of quantum systems. And they also have a claim since the summer that they solve a problem in quantum computer in 2.5 hours with a 40 kilowatt an hour energy, which is just for the fridge. And then the best known classical analog, they look at the Frontier supercomputer, which is, I think, in Argonne, like in one of the US national labs. It will take like 3 years of continuous running to reproduce the results. So there's no point. And like 550 gigawatt an hour of energy. So huge energy gap, and already like a cool enough example of quantum, example of quantum material one can study in a quantum processor. Oh yeah, this is a bit more technical. What exactly they measure? They come up with a new observational tool called out-of-time order correlators, which actually was inspired by black hole physics initially, like from academia, and then they are able to take this as a new measurement tool to run it on a quantum computer, and then later generalize it for like various molecular problems. Yeah, this is actually a bit more technical result from them. This is kind of illustrates why. So one of the hardest thing in quantum devices, because it's so sensitive, quantum computer, whenever anything touches it from the rest of the world, like why is it hard to build a very good quantum computer? Because essentially any like little photon hitting it can destroy the quantumness. Like normal computers don't. If you have a memory, in your normal computer, like a light shining on it will not destroy the bits. Versus with quantum properties are very sensitive. So like a light coming and hitting it could destroy the quantumness and destroy all of the computation. In fact, actually, Google had a cool paper a couple of years ago where they observed once in a while, like computer will completely reset itself, and then they realized it's correlated with some crazy cosmic waves coming from the universe. That like it's just those cosmic rays are like powerful enough to reset the quantum device, and so it's super important to like isolate device from the rest of the world, like and the way you do it, you put it in a cryogenic fridge and kind of cool the rest of the environment. But now there are even efforts to put it inside very big bunkers to like kind of shield from the rest of the environmental like signals. But also you have to measure the right things in a quantum computer. So there's a lot of cleverness that gets into like what observables have a good signal in a quantum computer and which ones don't. So this is a bit for more technical people. And essentially they looked at like different types of quantum observables like correlators, and they realized this out of time order correlators, which are like very sensitive to quantum properties, are actually pretty amazing tool to measure in a quantum computer. And that was like the biggest development of the paper, that they were able to show huge quantum advantage if you studied the properties of materials with a specific observable or like measurement tool that you apply to a quantum device. And yeah, I think they made the claim of quantum advantage, and that claim still stands. And then more recently, they put out a paper also about like actually using it for learning molecular structure of practical molecules, and collaborated with Berkeley experimental molecular research team to show that quantum computer can learn various properties of materials if you like have a good feedback between quantum computer and experiment in a real laboratory. So yeah, they're proposing it as a way to learn material properties if you have a quantum computer, much better than with AI. Because AI is good for certain type of materials to learn the properties, but not all. If you have too much entanglement, AI starts to struggle. If your material is very quantum, very entangled, like it's really hard to study with AI. And there's a lot of like research that went into that actually, that like AI is only good for certain class of materials. Yeah, actually, next result was actually from Quantinuum team. This came out like a week ago. I was in Quantinuum's announcement in New York for a big launch of their new processor, which is probably the most powerful quantum device that has all-to-all connectivity, like 98 qubits. And it's actually first illustration of discovering a new type of superconducting property in a quantum computer. And it's also beyond classical, so it's like there's no way you could do it with classical supercomputers. And it is actually much more commercially interesting problem, because like studying superconductivity and discovering superconducting materials is a very high value problem commercially. There's another line of work that IBM has been really pioneering in the past year. IBM devices are not in an advantage regime yet, but I think in 3 months they will be. Like I was just at the IBM event and they announced their new upgraded systems. So even though like anything current IBM machine can do, we can do with advanced simulation capabilities with classical computer. But next iteration will be impossible. So they're also entering that race of like quantum advantage. And one advantage IBM has, as opposed to Google and Quantinuum, they know how to make these machines at scale. So once they pass that threshold of quantum advantage, they're going to be able to build many machines and sell them to R&D teams in pharma companies, in government, in different institutions. And I think they're also so they might seem not at the top in a papers level, but I think next year they'll reach advantage and they will actually have several machines available for purchase at that scale. So I think they're still very much in a game and actually like pushing the frontier. And they have been doing a lot of work in like mapping computational chemistry problem to quantum. So they wrote this article, which is quite nice, that they came up with a new clever algorithm. Specifically, I think Mario Motta led a lot of this effort from IBM team, where even though quantum computers with like 100 qubits and then 10,000 operations cannot solve the full problem of computational chemistry, they came up with a quantum assisted framework where you could actually solve sub-problems of your original problem in a quantum computer and feed it into classical pipeline. And it would actually solve the whole thing like 10 to 100 times better than just classical algorithm. And that is more like this heuristics. Once you have these new machines which are capable of moving, manipulating, entanglement, doing completely different operations, it's very like not obvious where the heuristic methods will work. This is one of the early examples. We ourselves actually have a paper coming out very soon with where we applied this method to Quantinuum devices and actually got even better results, where how heuristic helps to accelerate like quantum chemistry modeling, like understanding the ground states of different molecules, which are like classically quite challenging. So yeah, this is actually another like huge area for computational. So condensed matter is one, like computational chemistry is another one. One I didn't put any slides in, but I think it's also very exciting, is actually high energy simulations as well, which is related to condensed matter. A lot of research team like Martin Savage, who has one of the best computational nuclear physics team in University of Washington, his team has been pushing a lot of effort to understand how quantum algorithms can be used in understanding fundamental particle physics and modeling them, because a lot of the things in particle physics are strongly coupled, highly entangled, highly correlated, and those things are really, really hard to predict classically. So you have to build a like CERN, do a big experiment and see the measurement outcome. Versus with large-scale quantum computers, you could run those experiments really quickly. Another area that's pretty exciting, I think in this area, it's much more closer to more classical problems, is like solving optimization problems. So quantum computers are likely going to be pretty amazing at very like non-convex, like really hard optimization problems, which are not data heavy, but the search space of all possibilities is like really large. And there has been really cool results in a past year again. Like in this area, we don't have like a clear advantage where quantum solves a problem that's impossible classically, but we can see substantial speedups coming from quantum devices on top of like state-of-the-art like classical solutions. Like actually, our team, BlueQubit, had a DARPA award last year where we developed an algorithm where we like looked at this graph optimization problem of 2D random graphs. Yeah, it was a toy model of a realistic graph problem, but like well-defined isolated example. And then we actually developed a new type of algorithm to run on a neutral atom quantum computer. And what we saw that for random graph instances, like quantum plus classical was able to solve the problem like almost 10 times faster than purely classically. So that is already pretty exciting by itself. Even though it's not like unsolvable, it's still in a regime that classically is solvable, but the speed ups are getting quite substantial to actually make sense to use quantum algorithms and quantum computers in these optimization routines. And I think as the devices get better, we'll very soon hit a limit where we could have clear advantage where quantum can solve it and then classical cannot for optimization problems. On this domain of like actually problems that are impossible Um, Classically, so I am going to advertise our new paper that has gotten some attention from academics and quantum teams in industry. Is a first claim of heuristic quantum advantage. Yeah, the paper is on arXiv. Yeah, you can check it out if you're interested. And this is actually an encryption protocol that we have developed. So essentially, like you are able to build. We take some classical secret, right? Like a message, a secret. We have a procedure for encrypting this secret into a quantum circuit, quantum algorithm. And then the whole point of the paper that quantum computers, like specifically like Quantinuum's H2 quantum processor with a 56 qubits and 2000 operations, can decrypt the message in 1 hour. So it's really quantum device can easily find the secret message we have encrypted. But best known classical algorithms that, at least to our knowledge, and we have done some exhaustive search of possible attack strategies, we expect will take years in large supercomputers. So it's like really ginormous gap between quantum and the classical. And this is actually pretty interesting example of what people call verifiable quantum advantage, where you already know the secret and you can actually verify that the quantum device found the right secret and use it for quantum benchmarking. But also it's a new way to do encryption with a quantum device. Yeah, this is kind of a more of a technical slide where like it shows how with the number of operations, like if you go from few hundred quantum operations, like classical algorithms, like approximate classical algorithms, like can still decrypt the secret. But once you hit like few thousand quantum operations, there is so much entanglement in your circuits that is impossible to do classically. So, and all classical methods like blow up exponentially versus quantum computer, it takes exactly the same 1 hour as it took for like small number of encryption gates. So this is like first of all, this is a method for validating that somebody has actually powerful quantum device, like a benchmarking that they have a powerful quantum device, but also can potentially be used as a new way to encrypt and decrypt the message, where only person who can decrypt it is a person who has a certain type of a quantum computer. So no other classical compute can decrypt it. Yeah, cool. This is my kind of summary slide. One of the main reasons of the talk was to reach out to different academic groups in here and kind of bring up like the progress on a quantum hardware and access and various opportunities. I think the access is going to keep getting better through national labs, through like clusters inside universities. I think quantum is going to be a big part of like computing centers in the next like 5 years, particularly for academic institutions and national labs. And it's a huge space for like discovering new approaches, new algorithmic approaches. And the key main domains, as I said, is like computational material science, computational chemistry, high energy physics simulation, and optimization. I think those are areas where new clever algorithms could change potentially like how we do things in these domains, could completely disrupt these domains. I compare it kind of a little bit to the stage when DeepMind had done AlphaGo and then AlphaFold. Like nobody was expecting how disruptive it's going to be for like a lot of the like polymer research and drug discovery, but the effects were tremendous. I think quantum computing will have similar effects in several academic fields that I mentioned, and maybe there are other algorithmic ideas that will apply to other fields too. I think in those fields, it's like the use cases are pretty like obvious and clear. I think a lot of cleverness should go into how do you make an interesting scientific problem and fit it into current state of a quantum computer. I think that's the biggest limitation, and this like limitation like is going to expand like in the next couple of years. Every year we add more qubits and more operations that gives you more flexibility to develop a new type of algorithmic approach for simulation. And also, I think there's a lot of interest from a government and defense in this area. I think like a DoD just put out a list of top priorities for them. I think quantum was one of them, which is quite exciting for quantum community. I think the research and investment in this area will continue as well. Yeah, and this is my email and my LinkedIn. Yeah, feel free to shoot an email if those topics are of interest to you guys. Yeah, with that, I'll wrap up and open.